We can use this information to develop a relationship known as the flexure formula. So let's take a look at what we know so far. So far, we developed this deformation geometry for a beam with a constant cross-section. Right? That's kind of important. The other thing about it is the cross-section and the bending is symmetrical. Right? It's symmetrical above that XY plane. Now, next thing we're going to put into this is Hooke's law. And if you recall, Hooke's law implies that for elastic deformation, stress is equal to modulus times strain. We're going to apply that to our longitudinal strains to develop longitudinal stresses. So here we go. We have our stress is equal to modulus times strain, and we know that strain is equal to minus y, right, the vertical position, divided by rho, rho being our radius of curvature. When we combine those two, it shows us that stress is going to be equal to negative times the modulus times y divided by rho. And what this essentially means is, much like our strain, we can show that bending stress is proportional to the distance from the neutral axis. Right? Again, we use that negative sign to correct for the tension versus compression, and it's going to be inversely proportional to the radius of curvature rho. So what does that look like in terms of a distribution? Well, if you recall, at the neutral axis, we have no stress, right? And as we move away from it, we see that the stress varies linearly with distance. Right? So we actually have a triangularly distributed stress where the maximum stress is at the surface. It drops to 0. Right? This is compression at the top. This is tension at the bottom. Right? And in terms of our position, we'll have y. C is going to be the distance to the actual surface. And at that surface, we have sigma max. Right? So maximum stress occurs at the point farthest from the neutral axis. It's going to be a distance c. And keep in mind, our stresses are going to follow this relationship. We already developed this. So we can show that our stress is going to be equal to the maximum stress divided by c. That essentially shows us what this slope is times y. So we can use the similar triangles here to show any point in here with this relationship. Now, in terms of where exactly is that neutral axis, or for that matter, that neutral surface, keep in mind that the object is not getting longer or shorter overall. So the sum of these forces must be equal to 0. So it turns out that the magnitude of the compressive forces here at the top have got to be equal to the magnitude of the tensile forces down here. And they need to essentially cancel each other out. And where they're canceled out is here at this neutral axis. So we can do an analysis where we look at a small element, delta A, we look at our force, delta F, the force on that small element. Keep in mind, force is going to be equal to stress times area, so we can relate those two together. And if we go through and integrate over that surface, it can be shown that the neutral axis is actually at the centroid of the surface. The centroid of the surface is the geometric center of this object. Now keep in mind that is for homogeneous beams, all of the same material. If we have beams made up of different materials, it gets a little bit more complicated, but for now we'll assume that our beam is homogeneous, and so it's going to be acting at a centroid. It also can be shown that from the moment analysis, right, because keep in mind these moments have to cancel each other's out, that the bending stress sigma, right, is going to be equal to our moment, right? This is the bending moment on the beam, negative times the bending moment on the beam times y divided by I, right? So this is the moment at that point divided by the moment of inertia at that point. Right? Also, we should note that the maximum stress is going to be at the top and bottom surfaces. This is going to be that distance c. So as we move further away, as y goes to c, our stress is going to go up until it hits its maximum at that surface. Now, if we look at the stress distribution across the cross section, turns out that we need to have a force couple that's generated, right? Keep in mind the top surface oftentimes is going to be in compression. That's going to be force acting in one direction. The bottom surface is going to be in tension. If you summed up the effect of the distributed forces, that's going to create another force. These need to be equal and opposite. That's what's known as a force couple, and they're what make up the bending moment. So they're going to act in the same direction that causes this bending moment. Now, keep in mind, if we look at back to our sign convention, a positive bending moment is one that's going to produce compression at the top and tension at the bottom, right? That's that idea of it being able to hold water. On the other hand, the opposite is true. If you have a negative bending moment, this is going to be a beam that's bent upwards, of course, would not hold water. So the reverse is also true. Now, if we go back and look at our equation, we can show that our moment is going to be equal to our negative times the maximum stress divided by C. Remember, this occurs at the surface C times our moment of inertia I, or we can reorganize this. So our maximum stress is going to be equal to minus m times c divided by I. Now keep in mind this minus sign is just all about the sign convention, right? If we were to take into consideration the fact that we already know that the maximum compression load is going to be at the top surface and the maximum tensile load will be at the bottom surface, we can eliminate that negative sign and we just show that sigma max is going to be equal to mc divided by I. Of course, this is just the magnitude, and of course the sign, whether it's positive or negative, compression or tension, is something you would need to take into consideration. Now, this equation is known as our flexure formula, right? And essentially, it's what's used to take our information of our beam, particularly our bending moment, and calculate the stress value. Right? In particular, it gives us the maximum normal stress, because usually we are looking for where the stress is at its highest in terms of strength analysis, and it shows us this is going to be directly connected to our bending moment M. So wherever our bending moment is at maximum, that's where we're going to have our maximum normal stress. We can also look at our stress at any point on that cross surface, right? And so the same applies, that stress is going to be equal to m times y divided by I. Again, m is the bending moment, y is the distance from the centroid, and I is the moment of inertia for the beam shape. So this is going to give us our normal stress at any point on the cross section. Again, we measure y for the neutral axis, and of course the bending moment. And you need to determine the sign of the stress by inspection. Again, if it's above the neutral axis, our beam is most often going to be in compression, so that will be negative, and below the neutral surface, our beam is going to be in tension, so that will be positive. So let's do a quick review about the units involved in the situation. Keep in mind we have a bending moment M, right? Bending moment M is going to be the effect of a force acting at a distance. So if we have US units, it'll be in inch pounds or potentially foot pounds. If we're dealing with SI or metric units, it's going to be in Newton times meters. Similarly, our distance Y, remember Y is the distance from the neutral axis, that's going to be a length unit, so it'll be inches or meters. And in terms of our moment of inertia, I, this is going to be inches to the fourth or meters to the fourth, right? Keep in mind when we go through and solve for that, that's our units for moment of inertia. As a result, if we take a look at our normal stress, remember it's moment times y divided by I, so inch pounds times inch divided by inches to the fourth. That gives us pounds per inch squared, or PSI, right? That's our correct unit for stress. And if we're dealing with metric, it's newtons times meters divided by meters to the fourth. This reduces to newtons per meter squared, which is just pascals. And again, our proper unit for SI stress. And of course, you could definitely use your SI prefixes, kilopascals, megapascals, gigapascals, etc. So keep in mind that the bending that we've done so far has been developed for pure bending only, right? But it turns out that the formula can be shown that it can work for whenever we're dealing with a situation, even if shear is there, right? So shear is another effect we'd have to take into consideration, but it doesn't need to be a pure bending situation for the flexure formula to apply. So far we have been looking at symmetric beams going through symmetric bending. But what happens if we have unsymmetric beams? So for example, if we take a look down here, we have beams where we have this L shape or this S shape with varying flanges at the top and bottom. These are clearly not symmetric. When these bend, they are not going to follow that nice distribution that we have been showing all along because our areas are varying, etc. So that needs to be taken into consideration. We can also have situations where the beam is symmetric, like here, but our moment is not applied exactly along our neutral axis. So if that's the case, if it's misaligned with the neutral axis, what's going to happen there? Even though the beam is symmetric, the bending itself is definitely not going to be symmetric. It's not going to be symmetric about the neutral axis, at least. Turns out that our flexor formula can be applied to these problems as long as we're careful about some of the things we define and about how we use it. So if the cross section is not symmetric, that's okay. We can do that. Again, not symmetric about the neutral axis. We just need to develop a process for it. And then there's a couple of different tricks we can use if it turns out the resultant moment about the axis is not about the neutral axis. How do we handle that situation? Let's take a look at the unsymmetric bending caused by an unsymmetric shape. For example, the one shown down here. Now, a couple things we need to take into consideration. For one, we need to define the origin at the centroid, right? So origin is going to be at our centroid. You need to go through and analyze the surface to determine that. We're also going to find y and z as the principal axes here. So that's important. Now, another thing we showed previously is if you were to sum up the stress distribution over the cross section, it's going to sum to be equal to 0, right? In that case, the stress caused by the upper compressive side has got to counteract the stress caused by the positive tensile side down here, right? This, of course, forms that bending moment M. Right? These two combine form that. So, but the sum of these two is going to be 0. And in terms of the sum of the moment about y, it's going to be equal to 0. These are shown by the following sets of equations over here, where our resulting force is going to be the sum of the force in the x direction. That summed over the entire area is going to be equal to 0. We also have the sum of the moments about y. That's going to sum to be equal to 0. And then, of course, the sum of the moments about z is actually going to be our bending moment m, right? So there's our moment about z. Z is our neutral axis right here, right? And of course, it's going to have a negative force up here, positive force down here. These are going to sum up to our bending moment. If you look at our normal stress, right, see it still varies linear with the maximum stress occurring at the surface, right? So maximum compression at the top, maximum tension at the bottom. And in terms of our analysis, again, directly from our flexure formula, stress is going to be equal to minus y divided by c, where c is the distance to the surface, times sigma max. So very easy to deal with our unsymmetric shape. It's all about finding the centroid. Now, to go back and take a look, we know that the moment caused by the stress distribution about y has got to be summed to be equal to 0, right? If we integrate over that entire surface, we know it's going to be summed to be equal to 0. That integral is known as the product of inertia. Right? And keep in mind, it's only 0 if we choose y and z in the right directions as our principal axes of inertia. To determine this, we actually use what are referred to as inertia transformation equations. You can take a look in your textbook Appendix A, and those are used to determine the y and z axes in this situation. Right? Now, keep in mind, if the area is symmetric, right, our principal axes are just going to be oriented along the axes of symmetry. Right? So in this case here, if we can define a symmetry here, we can show that our principal axes are aligned along that symmetry where this is a reflection over this. Right? So pretty straightforward where our principal axes are if we have a symmetric beam. Now, what happens if our unsymmetric bending is caused by an arbitrary applied moment? So instead of having the moment applied aligned with the z-axis or the y-axis, it's just aligned with some random direction in the plane. Well, it turns out we can again use the concept of superposition in that instead of trying to solve the stress distribution caused by the moment, let's instead divide the moment into two components. One, a moment about the z-axis, and second, a moment about the y-axis, and then apply the flexure formula to each of these separately. Right? So if we look here, if we look at just the effect of m sub z, this is the moment about the z-axis, we can use the flexure formula down here that it's the moment about the z-axis times y, again y is the distance above or below the z-axis, divided by I sub z. Where I sub z is again our moment of inertia, but this is about the z-axis. Right? It would look something like this. We've seen this before. Keep in mind you got to include the minus sign because y is defined positive, while unfortunately the stress of the upper portion of the beam is negative. So we could keep that minus sign there. Similarly, we can look at m sub y, which is the component about the y-axis. This will also cause a stress distribution where a portion of this will be in tension and a portion of it will be in compression. Right? This could be defined using the following flexure formula application: m sub y times z divided by I sub y, where of course I sub y is the moment of inertia about the y-axis. Now, because these two are both elastic and one does not affect the other, we can just sum those using superposition, so the total stress will be the effects, the stress caused by the moment about the z-axis plus the stress caused by the moment about the y-axis. And if you look at this graphically, you take this effect, and when you add them together, you will definitely get a different amount. Keep in mind, neutral axis is the axis where we have zero stress, so it's where these two, when added together, form an axis of no stress. All right? So it's a relatively simple multi-step process for determining what the bending stress would be by a arbitrarily applied moment. An alternative approach would be to determine the actual orientation of the neutral axis. Again, if you take a look at this diagram, if you see neutral axis has a stress value equal to 0, and you'll notice the stress varies linearly with the distance away from that. So if you know where our centroid is and you know the angle of the neutral axis, you can easily determine what the value of the stress is at any point on the surface. Now, to accomplish that, if we take a look at our definition of neutral axis, again, it's where the stress is equal to 0, we can easily show that y has to be equal to my times iz divided by mz times iy all times z. Right? Because they have to be equal to 0 because they have to sum together. Remember back to the previous equation, so they need to cancel each other out. And if you take a look, we know that m about z is going to be our moment times the cosine of theta, while m about y is going to be m times the sine of theta, where theta is the angle at which the moment's applied. then we can easily calculate the orientation in the neutral axis. In this case, tangent times phi, where phi is the angle of our neutral axis, is just going to depend upon the two moments of inertia, I sub z divided by I sub y times tangent of theta, where again theta is the angle of the moment is applied on the surface. Now, the last of the items we're going to cover in this chapter is on stress concentrations. We already talked about stress concentrations when it comes to tension and when it came to torsion. And the fact is, when dealing with bending, stress concentrations are also a problem. Fact is, anytime you have some sudden change in the cross section that may be caused by something like a notch, a hole, or a change in dimension, we're going to have an increase in the amount of stress. The fact is, there's no way to theoretically actually determine this, so what we have to rely on is these experimentally derived charts here. All right, so for example, here's a chart where we have a step down in the height of the item. Here's a chart where we have these U-shaped notches. The key thing about stress concentration is if you were to look at the stress distribution, you would find that it's no longer linear. In fact, the stress concentration causes it to be excessive in that one location, and you see that it actually goes much higher than that linear calculation. In terms of calculating that, we use a similar technique that we used with our other stress concentrations. We would still use our Flexler formula, mc over I, but then we'd modify it by this constant K. And in terms of the K, that would come from one of these contour lines depending upon the ratios associated right here. So in this case here, for example, you'd look at W versus H, that's going to be a certain number, in this case 4. If you had that, that would cause this, use this curve. You look at your ratio of radius to height, and where those two things cross, that gives you your stress concentration K. Notice it's always above 1, and unless you have very extreme situation, it kind of maxes out around 2. Now, these notches, on the other hand, are a little bit different. Still about 1, but can maximize out at about 3.4. So it can have a very strong effect. So you need to take these into consideration if you're dealing with a beam with any kind of notches in the side. This is very, very damaging. Holes are less so a problem. Keep in mind, if you recall, the stress value is maximum at the surface. So the further you go out with these kind of discontinuities, the more effective they are. So you'll notice in any kind of building technique, if you're going to use drill a hole through a beam, for example, for plumbing or electrical, they always want it in the middle or in the upper section where it's going to be under compression, so it actually closes that hole up. Now, there are other sections in this chapter I recommend you take a look at, particularly about composite beams, but we will not be covering due to limitations in time.